Welcome to Team Alpha's presentation on compensation ratio analysis. Our presentation today will cover a general overview of our final analysis on compensation ratios for Good Samaritan Society. The outline of today's presentation is found here. First, we'd like to explain what a Compa ratio is. A Compa ratio measures the relationship between the salary of an employee and the midpoint of the pay range for that specific employee's position. So if somebody is earning the exact amount of the midpoint of their salary range, their Compa ratio would be a 1.0 or 100%. Anything less than 1 means that they're earning less than the midpoint. Anything more than 1 means that they're earning more than the midpoint. So let's say, for example, the salary range for somebody's position is $40,000 to $80,000. That would put the midpoint at $60,000. If somebody's current salary is $55,000, their Compa ratio would be $55,000 divided by $60,000 being the midpoint, and that would equal a 0.92 or 92% Compa ratio. The goal of the work that we were asked to do around Compa ratio is to maximize the effectiveness of staff, minimize turnover, and extend the average length of employment by utilizing the Compa ratio in relation to the other variables that we had access to. So the objective of our work was to analyze those different variables and their correlation, predict the Compa ratio that will keep the best employees the longest, and prescribe that range of Compa ratio to reduce the risk of early exit. The background research that we conducted for this particular analysis is outlined in our final analysis. We used R and Rattle for statistical and descriptive analysis, Tableau for data visualization and predictive analysis, Rattle for model building and iterations, and R bloggers were learned for practical models and their implementation in real-world environments. In the design of our analysis, we used descriptive, predictive, and prescriptive techniques. For descriptive techniques, we used statistical analysis, correlation of variables, and graphical summaries. In predictive analysis, we use linear regression, decision tree modeling, random forest boosting, logistic regression, multinomial linear regression, and time series analysis. In today's presentation, we'll go into the ones that are highlighted in red: decision tree modeling, logistic regression, and time series analysis. All of this information led to our prescriptive analysis. Our data set came from the Good Samaritan Society. It was stored in a software system called Lawson, and it was able to be extracted into a Microsoft Excel file. Each row of the data acquired is a different employee that we had to work with, and it was only with the corporate office employees who were currently employed or had terminated within the last 7 years. Employees that were terminated prior to 7 years ago were purged from the company's systems, which is in alignment with government regulations on record retention. When we acquired the data, we had 28 variables and 1,395 observations in the data set. Much of our time in data exploration was in regards to checking, cleaning, and understanding data. It's often said that 80% of data analysis is spent on that cleaning and preparing of data. From there, we started with the statistical analysis of the data using the summary command. It's a quick way to get the usual summary of data. As we stated before, it started with 1,395 observations and 28 variables. After we cleaned and analyzed and understood the data further, we ended with 12 variables for our final analysis, down from 28. As part of our data exploration, we looked into missing data in our data set. The important missing observations include Compa ratio, pay grade, and termination date. The percentage of missing data for our current data set is insignificant in terms of the total volume of data, except for termination year, which had 54% data points missing. One part of our descriptive analysis was using statistical analysis. Reviewing our data, we found that the median of Compa ratio is 0.87. The average is 0.86. We found that 25% of the data lies below 0.80 Compa ratio, and 75% of the data lies above that 0.80 Compa ratio. That tells us that out of 1,285 employees, about 963 employees have a Compa ratio that is above 80%. An important part of our descriptive analysis was to use data visualization to get an understanding and a feel for our data. The next few slides will show some different data visualizations that we use to understand our data further. We ran a package in R called Choreogram. We can see from the correlation for these numerical values that there's a strong correlation between pay grade and the term year, and there's a strong negative correlation between the length of employment and the hire year. The term year, rate of pay, and age variables also play significant roles in our data set. On this particular slide, we can see that the term voluntary employees, which is the TV status, have a higher Compa ratio than active full-time employees. And although white employees are the majority in the corporate office, they don't have a higher Compa ratio. In fact, black employees have a higher Compa ratio than white employees. On this particular slide, we looked at the Compa ratio in bins and the average length of employment and the rate of pay. So what this visualization shows is that the green means that they stayed at the organization the longest. The line is the average rate of pay. And what we found is that although people have a higher comp ratio or have a higher rate of pay, it does not mean that they stay the longest. In fact, we found that there's a sweet spot right in the middle of people who stay the longest in the organization. To transform our data, since we had so much missing data and duplicate data really in our data set, we transformed our data through eliminating duplicate variables. We aggregated the hire dates into hire years and bucketed them into the year column instead of into the individual dates to allow us to project future easier. We did the same thing with term dates and the term year. And then we deleted just unnecessary variables, for instance, the zip code. We didn't feel like we needed that for our data analysis. Another way we transform the data is through looking at the data with and without outliers. We analyzed our time series exponential smoothing with and without outliers. We used a percentile range to exclude the outliers, and rather than just describing the observations of Compa ratio outliers, we used binning to check which Compa ratio is the best fit in our model. Our team started with 6 models. 3 of the models that we've outlined here are the key ones that we utilized. The remainder can be found in our full analysis. The decision tree model was an easy to understand model. It works with numerical and categorical variables, and it also does well with missing values, and that's why we used the decision tree model. We chose logistic regression to have a binary outcome, and because we wanted to see what our analysis would look like with a non-linear model for classification. And then finally, we looked at time series analysis. The idea here was to be able to project the future 5 years and what Compa ratio should be utilized by the organization to provide the best outcomes. For the decision tree model, we performed 4 different iterations with different key predictors. Shown here is the final version with a root node error of 2.27%. We always kept in mind that decision tree model tends to produce a higher error rate, and it's really a trade-off between simplicity and the error rate. The predictors that we used were employment length, age, and rate of pay. For logistic regression, we used the binary outputs of Compa ratio less than 80% as a 0, anything greater than 80% as a 1. So that's where our true and false came from. For our iterations, we used 2 different iterations, as you can see in the top chart as the number 1 and number 2 for model 1 and 2. The p-value indicates that the reduced model with fewer input predictors of status, rate of pay, and pay grade is the better fit of the 2. For our time series analysis, we ran through multiple iterations using different percentiles to see how that affected the R-squared value, the Compa ratio, the mean squared error, and the polynomial trend degree to get it with a high level of confidence. Since one of our goals was to predict the best Compa ratio, we felt like we needed to provide a range in this particular model. So our workforce team at Good Samaritan Society would have a minimum and a maximum range that they should stick within when offering salaries to new employees. For our time series analysis with exponential smoothing, we decided to use 2 outputs from our final result, one of the 25th percentile and the other one of the 95th percentile. This will provide a range of Compa ratios for that HR team. And although the results from the mean squared error on the trend shows that the best outputs are the 25th and 75th percentiles, we felt like it was too small of a range for practical use, so that's why we went with the 25th and 95th percentile. Here's the visualization of our 95th percentile time series analysis projecting out the future 5 years. That's the gray box in the front there. We found that this model may be significant as the p-value is less than 0.05. This is the data visualization for the time series analysis of the 25th percentile. Once again, this model might be significant at a p-value of less than 0.05. And on this slide, you'll also see that we created a Tableau link for the descriptive and predictive analysis by exponential smoothing. It is a dynamic link that the HR team can use to project the next 5 years, and that link is found on the left side on the bottom of the slide. Here you'll see the reference for our model performance for exponential smoothing with the 95th and 25th percentile. We can see that the alpha value is low, and that means that the model emphasizes on the recent data, and we did not use seasonality on the model building. To avoid overfitting of our data, we were very careful when we chose our variables. If we kept on adding those predictors, we felt like it was very likely that we would end with a high R-squared value, as we saw in our linear regression model. So before we started any model, we adjusted those predictors ahead of time. Another way that we avoided overfitting was in our time series analysis model. When we selected our range, we took into consideration the polynomial trend degree. The minimum and maximum of the range went to the 6th degree, while the range that we selected only went to the 3rd degree. We felt like the 6th degree could be an indicator of overfitting of the data. As our team tuned our analysis, we completed a couple different iterations for each model and continued to check the adjusted R-squared to find the best one. We also, like I indicated previously, checked the polynomial trend degree just to make sure that we were not overfitting the data. And we did fine-tune our analysis between the intermediate results and the executive summary. And the reason why we did that is because the original range of Compa ratio that we provided, we felt like was actually too wide of a range for practicality for the human resources team. So that's why we limited it to the 25th percentile and the 95th percentile for the lower and upper limits of the range. Resampling methods often involve repeatedly drawing samples from a training set and refitting the model of interest on each sample to obtain additional information about the fitted model. Some of the most common ones are cross-validation and bootstrap, and we did not use any of those models here. We wanted to keep that for future work, especially the leave one out cross-validation. When looking at class imbalances, we did use a classification technique in our logistic regression with one class less than 80% Compa ratio. The other class was more than 80% Compa ratio. The ratio of those two is 1 to 12, and we don't have a way of getting more data that would count and adjust that ratio, so we had to carefully check our confusion matrix, which is found in our full analysis, and that's what we felt like was our best way to check the classification performance. In the future, though, we could cross-check with a resampling technique. Our choice for that is the leave one out cross-validation. For predictors performance, rather than going with a complex method, we checked the predictors performance using a simple check. We checked each explanatory predictor by the adjusted R-square before we would start any model. And for each model, we knew how much the predictor was significant by the number of stars on the right-hand side based on probability. And then we would also check the ANOVA for predictors. For the logistic regression specifically, we created 2 different models with different predictors and compared those with ANOVA. Here you'll see an example of our linear regression model and how we reviewed the predictor's performance. To sum up our analysis, the descriptive analysis quickly showed us that females outnumbered males. Females have a higher Compa ratio in comparison to the male counterpart. Also, although white employees are in the large majority of the organization, Black employees have a higher Compa ratio in comparison. The data also showed us that employees who have been with the organization the longest have a Compa ratio ranging from 1 to 1.3, and this gave us a critical insight that the higher the Compa ratio does not directly attribute to the higher length of employment. As we stated previously, for the predictive analysis of our project, our team completed a time series analysis with the technique of exponential smoothing. It was used to develop a model to forecast a range of Compa ratios as an upper and lower boundary to utilize over the next 5 years. The model that we utilized will utilize employee data to prescribe that range of Compa ratio, and it would be both a win-win for the company and the employees. What we found is the minimum prediction over the next 5 years is 0.78, And the maximum prediction is 1.01, and that's after we removed the outliers. The other two models that we heavily looked at were logistic regression and decision tree models, as those gave a single Compa ratio output. From the decision tree model, we found the best results were at a 0.86 Compa ratio. And with logistic regression, we found that the best outcomes were delivered at a ratio greater than 0.80. And both of those outputs fall within that optimum range that was provided by the time series analysis with exponential smoothing, and that's why we moved forward as our suggestion with the time series analysis with exponential smoothing. In conclusion, human resources in an organization with 24,000 employees, like Good Samaritan Society, requires flexibility to allow for adaptation to market changes. That's why our team feels that the model that best fits the needs of the organization is the time series analysis with exponential smoothing technique included. This will utilize employee data to prescribe a range of the Compa ratio that would be a win-win situation for both the company and the employees. For the next 5 years, the prediction is 0.78 to 1.01 in Compa ratio. Thank you.